In this video, I will walk you through free response question number 1 from the 2023 AP Calculus exam. This problem is primarily about the relationship between rate of change and amount. This problem is calculator active, so we will use our graphing calculator as needed. A customer at a gas station is pumping gasoline into a gas tank. The rate of flow of gasoline is modeled by a differentiable function f, where f of t is measured in gallons per second and t is measured in seconds since pumping began. Selected values of f of t are given in the table. Part A. Using correct units, interpret the meaning of the integral of f of t from 60 to 135 in the context of the problem. Use a right-Riemann sum with these three subintervals to approximate the value of this integral. Here is a fundamental concept I want you to memorize. The integral of a rate from A to B is the net change in the amount from A to B. Notice that f of t is the rate at which gasoline flows into the tank. So this integral is the integral of a rate. I told you that in general, the integral of a rate is equal to the net change in the amount. In this case, we have the integral of the rate at which gasoline pours into the tank from 60 to 135. So this will equal the net change in the amount of gas in the tank in gallons from t equals 60 seconds to t equals 135 seconds. Make sure you mention your units. You will lose a point on the AP exam on a problem like this if you don't mention gallons and seconds. This wording feels a little bit awkward to me. Let's see if we can get across the same concept in a more straightforward way. This integral represents the amount of gas in gallons that flows into the tank from t equals 60 seconds to t equals 135 seconds. Next, we will use a right-Riemann sum with these three subintervals to approximate the value of this integral. An integral of a function from a to b is the area under a curve from a to b. Using a right-Riemann sum to estimate this integral means using rectangles like this one to approximate the area under the curve. It's called a right-Riemann sum because the height of the rectangle will equal the value of the function on the right-hand side of the rectangle. We were told to use three subintervals, so that means we will need to use three rectangles to approximate the area under the curve. I've set up a column on this table for each rectangle. We know that the area of a rectangle is base times height, so I will have a row for the base of each rectangle and a row for the height of each rectangle. The base of the first rectangle is 30 because it goes from 60 to 90. Similarly, from 90 to 120 is 30, and from 120 to 135 is 15. Next, we need to find the height of each rectangle. Let's go back to that first rectangle from 60 to 90. The height of this rectangle will be the value of the function on the right-hand side. In other words, the value of the function at 90. Looking at the table, that is 0.15. Similarly, the height of the rectangle from 90 to 120 will be the value of the function at 120, 0.1. And the height of the rectangle from 120 to 135 will be the value of the function at 135, 0.05. So the value of this integral can be approximated by the sum of the areas of these three rectangles. So I'm just going to do base times height plus base times height plus base times height. And as long as you include your units, you can leave your answer just like this for full credit. However, if you're curious, that comes out to 8.25 gallons. So approximately 8.25 gallons of gas flowed into the tank between t equals 60 seconds and t equals 135 seconds. And that's it for Part A. Part B. Must there exist a value of c between 60 and 120 such that f prime at c equals 0? Justify your answer. Whenever they start talking about the existence of a value, that's your clue that you will probably need one of the 5 existence theorems. You definitely need to memorize these 5 existence theorems. So if you need a review, go ahead and click the link that appears in the upper right-hand corner, or find the link in the description. The 5 theorems you need to memorize are the intermediate value theorem, the extreme value theorem, Rolle's theorem, the mean value theorem, and the mean value theorem for integrals. I can just almost squeeze it in there, man. Let's use the process of elimination to figure out which of the 5 existence theorems we need. The extreme value theorem is about the existence of an absolute max or an absolute min on a closed interval. Part B has nothing to do with this, so we can eliminate this as one of the options. Of the remaining 4 theorems, 2 of them have a conclusion that mentions f of c, the value of the original function. One of them is the intermediate value theorem, and the other one is the mean value theorem for integrals. So 2 of them mention f of c in the conclusion. The conclusion of the other 2 theorems involve f prime at c, the value of the derivative. That includes the mean value theorem and Rolle's theorem. Both of these involve f prime at c. In part B, we were given data for f of t. So f of t is definitely the original function. But then we are being asked about the existence of f prime at c. This tells us we will either need the mean value theorem or Rolle's theorem. The mean value theorem tells us whether f prime at c will equal this average rate of change formula for some value of c. However, it is Rolle's theorem that states that f prime at c will equal 0 for some value of c, provided certain preconditions are met. So let's shoot for Rolle's theorem, but first we must establish that the preconditions have been met. For Rolle's theorem to apply, f must be continuous and differentiable from a to b. In the setup of the problem, we were told that function f is differentiable. But what about continuous? Well, if a function is differentiable, it is automatically continuous, but we must state this at the beginning of our answer. We must begin by saying since f of x is differentiable, it is also continuous. Kabam! The first preconditions have been met. The other precondition is that f at a must equal f at b. In other words, the value of the function must be equal at 2 different places. The given interval is between 60 and 120. So here's 60 and here's 120. Notice that the value of the function is equal at both of these endpoints. So this is our a and our b. We can establish that the second precondition has been met by adding, and since f at 60 equals f at 120, that's your f at a equals f at b. Now it's time for the conclusion. There is a c in AB such that f prime at c equals 0. We're just going to copy this conclusion into our answer. However, instead of saying a and b, we are going to use the 2 values that we just mentioned. We conclude with there is a c in the interval from 60 to 120 such that f prime at c equals 0. Notice that we didn't actually mention that we were using Rolle's theorem. You can get full credit without naming the theorem that you are using. If you did want to mention it, you would put it right here. So let's put it all together. Since f of x is differentiable, it is also continuous. And since f at 60 equals f at 120, by Rolle's, there is a c in the interval from 60 to 120 such that f prime at c equals 0. Part C. The rate of flow of gasoline in gallons per second can also be modeled by g of t, which equals this. On the interval from 0 to 150, using this model, find the average rate of flow of gasoline over the time interval from 0 to 150. Show the setup for your calculations. I see the word average right here, but we have learned about 2 different concepts that involve the word average. Average rate of change of f of x, which is given by this formula, and the average value of f of x, which is given by this formula. So before we go any further, we need to decide which of these two concepts are we being asked to find. It all depends on what G of t represents. If G of t was the amount of gas in the tank, we're talking gallons at time t, then the average rate of flow would mean the average rate of change of G of t. Notice that the average rate of change formula changes the units from gallons to gallons per second. The average value formula does not change the units. If f of x is in gallons, the average value of f of x is still in gallons. In this case, we want the average rate of flow of gasoline, which is clearly gallons per second. So if this were the case, we would want average rate of change of G of t. However, G of t is not actually the amount of gas. The units are not in gallons. Since G of t is the rate of flow of gasoline, finding the average rate of flow of gasoline means finding the average value of G of t. You can use the units as a guide. G of t is in gallons per second. We are looking for the average rate of flow of gasoline over time. That's also going to be in gallons per second, so we don't want the units to change. Between these two, average value is the formula that does not change the units. If G of t is already in gallons per second, average value will still give us gallons per second. By contrast, if we mistakenly used the rate of change formula, it would change the units of G of t from gallons per second to gallons per second squared. In other words, gallons per second per second. That's not the average rate. That's the average rate of change of the rate, not what we want. So we're going to use the average value formula, which I think of as integral divided by interval. The integral of G of t from 0 to 150 divided by the interval 150 minus 0. Dividing by 150 is the same as multiplying by 1 over 150. This is the way I prefer to type average value expressions into my calculator. Speaking of the calculator, I'm noticing that we are going to need G of t again for part D of this problem. It will save us a little bit of time if we type this in as a function in our calculator instead of typing it directly into the integral. So hit your y equals button and let's type G of t in as y1. So here's G of t typed into y1, except we had to use x's instead of t's. So now we need to hit second quit to get to a blank screen, and we want to type in this expression. So 1 over 150 times the integral. So here we have 1 over 150. For the integral, we need to do math 9. And it's the integral from 0 to 150. So here we can refer back to the expression that we have typed in y1. So we will not type in the whole function here. Instead, we will hit the vars button, and we will switch over to yvars, and hit enter for function. And we typed it into y1. So just hit enter again. So this y1 is really our G of t. And we just finish it off with a dx. And that's it. This will be the average value of G of t. So 0.096 if you round up, or 0.95 if you like to truncate. So the average rate of flow of gasoline over this time interval is 0.096 gallons per second. Make sure you include these units. You will lose a point if they are missing. By the way, on the AP exam, you don't have to show this first part. That was just for instructional purposes. You can just go straight to this. Part D, using the model G defined in Part C, find the value of G prime at 140. Interpret the meaning of your answer in the context of the problem. Since we already typed function g into the calculator as y1, finding g prime at 140 is going to be trivial, super easy. To evaluate an integral, we did Math 9. To evaluate a derivative, we will do Math 8. Go ahead and type an x in right here so we have d dx, the derivative of whatever function we put in here. We don't have to type in that whole function g of t, we can just put in y1. Again, we will do vars, switch over to yvars, hit enter for function, and pick y1. So this is the derivative of g of t at, and we are to evaluate at 140. So simply type in 140 right here, and kabam, negative 0.004 if you truncate, or negative 0.005 if you like to round. Remember that g of t is the rate of flow of gasoline in gallons per second. That's why g prime will be the rate of change of this rate. So the units will be gallons per second per second. In other words, gallons per second squared. Finally, we must interpret the meaning of this answer in the context of the problem. I'm going to do this in two different ways, and you can decide which way makes more sense to you. Here is a very direct way to interpret your answer. We know that taking the derivative of a function means finding the rate of change of that function. But since g of t is already the rate of flow, g prime will be the rate of change of the rate of flow. So we could say the rate of change of the rate of flow of gasoline at t equals 140 seconds is negative 0.005 gallons per second squared. Make sure you include both of these units, seconds and gallons per second squared. To me, a more natural way of conveying the same thing is to say at t equals 140 seconds, the rate of flow of gasoline is decreasing by 0.005 gallons per second per second. So instead of saying the rate of change of the rate is this negative number, I can simply say the rate is decreasing by this number.